Hi there, welcome to a quick video tutorial on modeling with exponential functions. In this video, what you're going to see is how to use exponential functions to model a given set of data, which is going to come from some sort of real-world scenario. In this one, we're going to look at bacteria and radioactive decay. If you aren't really up to date on exponential functions, there are a few videos that you can check out and then kind of pop back in and take a look. You should have a working understanding of what an exponential function is at this point, and then we can jump right into exponential growth and decay. All right. Okay, so exponential growth, talked about this a little bit, is a relationship where there's an increase by a factor. So some factor. In this example, we've got a type of bacteria that triples in number every day. So we're increasing by a factor of 3 every day. So on the day that you happen to start looking at these bacteria, your sample has a population of 100. So I'm going to let P represent your population, D represent the number of days. So at day 0, the first, as soon as you start looking at these bacteria, you see that there's 100 of them. So what your goal is to determine the population each day for the first 4 days. So I've done that in a table of values here. So essentially that's what I have, is a relationship between the number of days and the population of the bacteria. So you can see as each day increases, I'm increasing my population by a factor of 3. So I'm multiplying my population by 3 every day. Okay, so one way we can represent that is this table of values here with the actual population, but I can also represent that in a different way by taking my initial population and multiplying by 3 to the power of my number of days. Okay, so I'm going to do that in this chart here, and you're going to see why in a moment. So you can see that my first observation is I've got 100 bacteria, and I'm going to multiply by my tripling factor to the power of 0 for day 0. Okay, and I'm going to carry on in that way. So I'm going to multiply by my tripling factor to the power of 1 for the first day, because I've taken my initial population and I'm now multiplying by a factor of 3. They've tripled in numbers. On the second day, I've tripled in number from what I had previously. So I've taken 3 times 100 and I've multiplied by 3. So I've got this square here. And you can see that I'm going to carry on in that pattern as my days progress. So this table is really equivalent to this first table here. But the reason that I'm writing it this way is so that I can come up with a general equation for this scenario. Okay, we know that we have this initial population of 100. Our equation is going to be representing population. So we can say our population is going to be 100. We start with 100, but we're going to multiply by our tripling factor to the power of the number of days that we're interested in. So this equation here, this is a function. I can substitute in a number of days, and it will tell me my population of my bacteria. As it turns out, that's very useful because I could graph my exponential function. Okay, so I could come up with this table of values and plot my points. I've done that ahead of time just for the sake of time, but it's a good idea just to get used to graphing these sorts of functions, because what we're going to do next is start transforming them in a similar way to the way that we transform the basic functions in the previous unit that I did on my YouTube channel here. And being able to represent this thing as a function is kind of nice, because we can actually start predicting how much bacteria we'll have after a certain amount of time. So what I've done is I've got 2 quick examples here. I'm not going to spend too much time on these, but if I have this general function and I want to predict how much bacteria I'm going to have after 1 week, I can just substitute in 7. There's 7 days in a week, and I can determine that there are 218,700 bacteria in this culture after 1 week. So you can imagine I'm starting with 100 and I'm multiplying by 3 consecutively for 7 days. I'm going to end up with quite a bit of bacteria. And after 2 weeks, you can see I end up with even more. Okay, so that's just an example of something we call exponential growth, which is when we multiply by a factor. Okay, it makes sense here to talk about exponential decay. This is a relationship where you decrease by a factor. A great example is half-life, which is the length of time it takes for something to decay to 1/2 of its original amount. You see this with radioactive material and radioactive waste. So for example, uranium is commonly used as a fuel to power nuclear reactors. So we've got this 100-gram sample. It's got a half-life of 1 hour. So after 1 hour, you're going to have half of your original sample. And our goal is to find the mass after the first 4 hours. So this is a very similar example to the previous one, except this time we're working with exponential decay. Okay, so at time 0, I've started with 100 grams. 1 hour has passed. You can see I've decreased my sample by a factor of 2. And again, after 2 hours, I've decreased by another factor of 2, and so on and so on. And I can represent this in the same way that I did in the first example. I can take my initial sample, and I'm gonna write it as a product of my factor to the power of the number of days, right? So if my first initial observation has 100, I'm gonna multiply by 1/2 to the power of 0, and that should give me 100. After 1 day, I've decayed by a factor of 2, so I'm raising that to the power of 1. 2 days, I'm decaying by a factor of 2 from my initial decay, so I've got a power of 2, and so on and so on. And again, this allows me to generate a general equation which allows me to predict the mass after a certain number of hours. Okay, sorry, I just noticed an error in my let statement here. M is going to represent the mass. Sorry about that. So that'll be my general equation. Again, this is a function. I can substitute in the number of hours and I can predict what the mass will be. This is great because, again, I can graph this thing, get a visual representation of what's happening. You can see as time progresses, my mass decreases. Sorry, I don't have axis labels here, but you can see that there is that general decrease by a factor of 2. This helps me predict how much uranium I'll have left after a certain number of hours. If I want to find out how much I've got left after 12 hours, I can simply substitute 12 in for H, do a little calculation there, and you'll see that I've got 0.0244 grams left. So you can see that this thing is decreasing pretty significantly after 12 hours, where we've almost got 0 grams left. However, you'll see that it's not actually possible to get 0 grams left. And we're going to talk a little bit about that in some later videos. All right, so that's the end of this video tutorial. Hoping this helped as you start modeling with exponential functions. Looked at a couple real-life examples with bacteria and radioactive decay. Hopefully this helps as you move forward with your studies with exponential functions. Thanks for watching.